Hello everyone, today we're going to talk about how to do set theory, or at least the basics of it. We define a set to be a collection of things. For example, we can make a set out of the numbers 2, 3, and 5. The objects inside sets can be anything. Numbers, other sets, or things that aren't even necessarily mathematical in nature. Sets are a very fundamental concept that we all use in our everyday lives without even realizing it. For example, when we're thinking about the US Senate, we're really thinking about the set of people who are current US senators. It's important to study sets because of how often they show up and because they can be used to build more complicated mathematical objects. So in this video, we're going to take a look at how we treat sets mathematically, how to build sets from other sets, and how to prove statements involving sets. Before proceeding, I should quickly mention that we already saw two very important examples of sets in previous videos: the natural numbers and the integers. I should also mention that there is a very important set called the empty set, which is just the set that contains nothing. One way to represent the empty set is with a pair of curly braces that has nothing in between them. However, it is much more common to represent the empty set like this, with a circle with a slash in it. The empty set can appear when we try to build a set based on a condition, but nothing satisfies that condition. For example, suppose we consider the integers that are greater than or equal to 3, while also being less than or equal to -2. It's impossible for an integer to satisfy these conditions, so the set ends up being empty. There are also two rules for how we represent sets. The first is that the order by which we write the elements of a set does not matter. For example, the set 2, 3, 5 is exactly the same as the set 5, 2, 3. The second rule is that we don't write sets with duplicate elements. For example, instead of writing out the set 1, 2, 2, we would write out the set 1, 2. Now let's talk about how we talk about sets. We often refer to objects being present in a set. So we say that blank is an element of the set blank. For example, we might say that 2 is an element of the integers, and we would write that out using this trident symbol, which directly stands for, quote, is an element of, end quote. We also sometimes refer to objects not being an element of a set. For example, 2 is not an element of the empty set. In fact, no object is an element of the empty set. And when we say that something is not the element of something else, we express that using the trident symbol but with a slash through it. Don't forget that sets themselves can also be objects in a set. For example, we could say that the set 1, 2 is an element of the set on the right. It's also important to talk about when something is a subcollection of another collection, or in other words, when a set is a subset of another set. For a statement like A is a subset of B, we can write that in symbols as shown. We can visualize this with a Venn diagram, drawing A and B as blobs, where we think of any point inside those blobs as being an element of the corresponding set. So when we say that A is a subset of B, it's like saying that the blob A is completely contained within the blob B. For example, the set 2, 5, 6 is a subset of the set of natural numbers from 1 to 6. Or another example, the set of even integers is a subset of the integers. If we wanted to prove a statement like A is a subset of B, then we would have to show that for any element x of A, it follows that x has to be an element of B. Note that from this definition, it follows that every set has to be a subset of itself. Additionally, it's important to realize that the empty set is a subset of every other set. To prove this according to our definition, we would need to show that every element of the empty set is an element of all sets. But the empty set has no elements, so there's no work to do. We're done. Another way to think of this is that if there was a set A that didn't have the empty set as a subset, then this would have to be because there was an element x of the empty set that wasn't also an element of A. But this is impossible because the empty set has no elements to begin with. Thus, we again see that the empty set is a subset of every set. Finally, it's important to talk about when two sets have the same elements, or are in other words equal. To show that two sets A and B are equal, we would have to first show that A is a subset of B, and that B is a subset of A. If two sets are contained within each other, then this means that they have to be equal. Now let's talk about how we can build sets from other sets. There are 4 set building operations we'll talk about in this video. The first is the union. The union of 2 sets A and B is the set of objects that are elements of A or B. This OR is inclusive, so if an object is an element of both A and B, it's still in the union. The intersection of 2 sets A and B is the set of objects that are elements of both A and B. The complement of a set B in another set A is the set of objects that are elements of A but are not elements of B. And finally, we have the Cartesian product, which we will not talk about at this time, but we will cover later in the video. We will now take a look at some practice problems. And I know that we covered a lot of new information and definitions in this introduction. I don't expect anyone to instantly learn these definitions, so feel free to rewind the video and go back in case you forget something. The first problem: show that the union of the complement of B and A the complement of A and B is equal to the complement of the intersection of A and B in the union of A and B. To visualize what's going on, it can be helpful to draw Venn diagrams. Now, in order to prove the statement, remember that we have to show 2 things: that the left side is a subset of the right side, and that the right side is a subset of the left side. So now we tackle the first subproblem. Let x be an element of the left side. Our end goal is we want to show that this element x is also an element of the right side. First, we see we have 2 cases to deal with, based on whether x is an element of the complement of B and A, or if it's an element of the complement of A and B. If we are dealing with the first case, then x must be an element of A, while also not being an element of B. X is an element of A, so it's also an element of the union of A and B. Also, x isn't an element of B, so this means that it can't be an element of the intersection of A and B. Putting all this together, we see that x is an element of the right side, finishing this case. As for the other case, we see that x is an element of B, while also not being an element of A. The proof for this case is pretty similar to the last one, so I'm not going to show it. In either case, x is an element of the right side, thus showing that the left side is a subset of the right side. Now for the second subproblem, where we have to show that the right side is a subset of the left side. Let x be an element of the right side. We see that x must be an element of the union of A and B, while also not being an element of the intersection of A and B. Since x is an element of the union, we deal with 2 cases: x is an element of A, or x is an element of B. If x is an element of A, then because x isn't an element of the intersection of A and B, x can't be an element of B. Thus, x has to be an element of the complement of B and A, so it is an element of the left side. In the case that x is an element of B, the proof is similar to the previous case. In either case, x is an element of the right side, so the right side is a subset of the left side. Since both sides are subsets of the other side, we conclude that both sides are equal, thus finishing the proof. Now we move on to problem 2. A is a subset of B if and only if the union of A and B equals B. In math, we often abbreviate the phrase if and only if by writing IFF for short. To prove if and only if statements, we have to prove the statement in both directions. So we have to prove that if A is a subset of B, then the union of A and B equals B. And we also have to prove that if the union of A and B equals B, then this implies that A is a subset of B. Drawing a Venn diagram, we see that the statement as a whole amounts to the fact that if one set is contained within the other, then their union is the larger set. We start this problem by proving the first statement. We assume that A is a subset of B. And now we have to show that the union of A and B equals B. So we start by proving that the left side is a subset of the right side. Let x be an element of the left side, so the union of A and B. We again deal with 2 cases depending on which set x is an element of. If x is an element of A, then because A is a subset of B, x has to be an element of B. Case 2. If x is an element of B, then that's great, we're done. Thus, we conclude that the union of A and B is a subset of B. Now we have to show that B is a subset of the union of A and B. Let x be an element of B. Then x is also an element of the union of A and B. So we're done. That was pretty easy. So we conclude that B is a subset of the union of A and B, which combined with our previous result shows that the union of A and B equals B, as long as A is a subset of B. Now we have to prove the other direction. If the union of A and B equals B, then A has to be a subset of B. We assume that the union of A and B equals B. Let X be an element of A. Then X must also be an element of the union of A and B. But by our assumption, this equals B, so X must be an element of B. So we conclude that A is a subset of B, and we have successfully proven both directions of the original statement. Now let's move on to problem 3. If C equals the union of A and B, and the intersection of A and B is the empty set, then show that A equals the complement of B and C. Drawing a picture, we see this essentially amounts to the fact that if A and B partition a set C, then the complement of A or B is just the other set. So to start this problem, we suppose that C equals the union of A and B, and that the intersection of A and B is empty. We have to show that A equals the complement of B and C. So we first show that the left side is a subset of the right side. Let X be an element of A. Then we must have that X is also an element of the union of A and B. But by assumption, this equals C, so X must also be an element of C. We now have to consider two cases, depending whether or not X is an element of B. If X was an element of B, then because X is already an element of A, this would mean that X is an element of the intersection of A and B. But by assumption, this intersection is empty. So we reach a contradiction, and we see that X can't be an element of B. So we must have that X is not an element of B. So then this means that X has to be an element of the complement of B and C. So we're done. Now let's show that the right side is a subset of the left side. Let X be an element of the complement of B and C. So then X is an element of C, or in other words, X is an element of the union of A and B. And we also have that X is not an element of B. So then we see from the union that X has to be an element of A. Thus, we have shown that the right side is a subset of the left side. And combined with the previous part, we conclude that A is equal to the complement of B and C. So we are done with problem 3. We are now going to talk about the final set building operation that we foreshadowed earlier, the Cartesian product. We already mentioned that order does not matter for sets, but sometimes order does matter, in which case we use ordered pairs. We say that two ordered pairs are equal if and only if the corresponding entries are the same. So for example, the ordered pair AB would not be equal to the ordered pair BA unless A equals B. Also, it's not too important, but I should also at least mention the fact that you can build ordered pairs from just sets. There are multiple ways to do so, and one way is shown below. Even though the order of elements in a set doesn't matter, the trick is that we add an additional element to the set with B, so that we could tell which entry of the ordered pair goes on the right. This only works if A doesn't equal B. If A equals B, then the set collapses down to the set of A. In this case, the order of the ordered pair doesn't matter anyways, so it's fine. Now, we are ready to define the Cartesian product. The Cartesian product of two sets A and B is the set of ordered pairs, with entries in the first slot coming from A, and entries in the second slot coming from B. Another way to think of the Cartesian product is as being the set of ways by which we can pick an element from A and an element from B. If you have experience with graphing functions, then you've already seen examples of the Cartesian product. This graph, which we use to plot functions, is the Cartesian product between two copies of the real numbers. The real numbers, by the way, is just the full set of numbers that we normally work with. It has integers like 0 and 2, rational numbers like -2/3, and even irrational numbers like the negative square root of 5 and pi. Imaginary numbers aren't real numbers though. Let's look at another example. Suppose A is this set of 3 intervals, and let B be this set of 2 intervals. We can visualize the Cartesian product between these two sets as being the points in the plane that line up with both A and B. Now let's take a look at a practice problem involving the Cartesian product. We need to show that the intersection of A and B cross C is equal to the intersection of A cross C and B cross C. Using this diagram, we can visualize what each of the sets represent. The intersection of A and B cross C, A cross C, B cross C, and the intersection of A cross C and B cross C. Our first subproblem is that we need to show that the left side is a subset of the right side. Let xy be an ordered pair element of the left side. Then x is an element of the intersection of a and b, and y is an element of c. X is an element of A, so xy has to be an element of A cross C. X is an element of B, so xy also has to be an element of B cross C. Thus, xy has to be an element of the intersection of A cross C and B cross C. Now for the second subproblem, where we have to show that the right side is a subset of the left side. Let xy be an ordered pair element of the right side. This means that xy is an element of A cross C, and it's also an element of B cross C. We have that x is an element of A, and it's also an element of B, so x has to be an element of the intersection of A and B. And also, y is an element of C. Thus, xy has to be an element of the intersection of A and B cross C. So the right side is a subset of the left side, and since both sides are subsets of each other, we conclude that they have to be equal. That's the last of the practice problems for this video. But if you're looking more chances to test your understanding of basic set theory, I highly recommend trying out these 6 practice problems. Before I end the video, I want to talk a bit more about what we can do with ordered pairs. A very important usage of ordered pairs is to define relations. A relation between two sets A and B is a subset of the Cartesian product between those sets. If an ordered pair xy is an element of R, we interpret that as x is related to y according to the relationship in question. For example, let's define a relationship on the integers that represents less than or equal to. Then ordered pairs like -2, 3 would be elements of R, because -2 is less than or equal to 3. For another example, we could define a relationship on the set of people in the world, where we consider x to be related to y if y was born in the same year as x. For example, the ordered pair Karen-Jeremy would be an element of R if and only if Karen was born in the same year as Jeremy. There is a very important type of relation called an equivalence relation, which is a relation that somehow generalizes the notion of equality. A relation is an equivalence relation if and only if it satisfies 3 key properties. 1. Every element is related to itself. So for any element x, the ordered pair xx is an element of R. This property is called being reflexive. The second property is the symmetric property, which means that if x is related to y, then y has to be related to x. Or in other words, if the ordered pair xy is an element of R, then the ordered pair yx also has to be an element of R. Finally, we have the transitive property, which means that if x is related to y, and y is related to z, then this means that x has to be related to z. Or in other words, if xy and yz are ordered pairs that are elements of R, then this means that xc also has to be an ordered pair that's an element of R. Equivalence relations are important because they allow us to partition sets into subsets called equivalence classes, where each equivalence class is made up of elements that are all related to one another. We all use equivalence relations in our lives without even thinking about it, because sometimes it's important to break collections down into smaller ones based on a shared property. The second example of relations I mentioned is also an example of an equivalence relation. And this kind of equivalence relation would be important if you ever want to consider people that were born in the same year, like maybe for the purpose of a census or population data or something. The first example of a relation I mentioned is not an equivalence relation, because the less than or equal to relation fails to be symmetric. I'm not actually sure if we'll need to talk about equivalence relations in a video in the near future, but I felt the need to bring up equivalence relations now, so that you'll be prepared when equivalence relations become very important later on in your math career. Equivalence relations become very important in topics like abstract algebra when we're talking about isomorphisms, quotient groups, or tensors. Anyways, in this video we managed to talk about the basics of set theory, and next time we'll take a look at how we can build functions out of relations. But until then, thank you all for watching. Be sure to comment, like, and subscribe. Stay awesome, everyone. Bye!